So let's look at a few factors that affect solubility. So we'll look at common ion and pH. So if you have a common ion in your solution, that means one of your products you already have sitting around in the solution, and so your solid's not going to have to dissociate as much in order to reach equilibrium because you already have some of it present. So let's see, we can actually put some numbers to this and see what happens when you do that. So for example, so if we had barium sulfate here, and suppose I already had some sulfate ions, when not as much of this solid has to dissociate in ions in order to reach equilibrium. So remember, you know you're at equilibrium when the equilibrium constant expression is satisfied. So when this is true, when the barium concentration times the sulfate concentration equals a certain number, whatever that KSP is, then you've reached equilibrium. So if you already have some of this in your solution, you don't have to make as much. So the solid will become less soluble in the presence of a common ion. So let's try a couple of examples of this. So if we had calcium fluoride, they give you the KSP, which is not going to change. The KSP is always going to be the same. That's the constant. And so I set up the expressions for you already here. The K doesn't change, but the solubility will change depending on how much of your ions you have present in your solution. So the first one is just in water. That means you don't have any you don't have any common ions. You know, this is just for every one calcium fluoride you get one calcium, and you get 2 fluoride ions. Take these, plug it into your KSP expression. You have 3.9 times 10 to the negative 11 is equal to S times 2S, that whole thing squared, which is 4s cubed. 3.9 times 10 to the negative 11 divided by 4, and you get your s cubed is equal to something, 9.75 times 10 to the negative 12, and then you want to take the third, raise that to the 1/3 power, and you end up with S is like 2.1 times 10 to the negative 4 molar. Okay, so whenever you're finding that solubility, you want to find the molar concentration. Make sure you put your units there. That's kind of our baseline. So that's how soluble this would be in just water. Now, what would happen if instead of just having it in water, you have some calcium nitrate? So calcium nitrate is going to dissociate into some calcium ions and some nitrate. So you have some calcium, right? That's your common ion. So instead of having none of this, you're going to start off with a little bit, and you're going to add to it. You're going to make S, and here you're going to make 2S. And so at equilibrium, basically making a nice table. 010 plus S, and this is just 2S. So in the presence of a common ion, you have an initial concentration. You have 0.01 molar calcium ions. And then the S and the 2S, that depends on the stoichiometry, right? This is 1S, this is going to be 2, so I can make 2S. And now I can take this and plug that into the equilibrium constant expression. And even though you have, calcium nitrate, don't worry about the nitrate. The nitrate's not going to do anything. The KSP corresponds to this reaction. It's the solid dissociating into ions. This KSP never changes, but the solubility, the S, will change, and that's what we're going to see now. We're going to see how the S changes. So we have 3.9 times 10 to the negative 11 is 0.010 plus S times 2S, that whole thing squared. So when you simplify this a little bit, this would be a lot easier if I didn't have to worry about that S, right? And we know that that solubility is going to be small. It's going to be small because the KSP is so small. So I can ignore that S the way we usually do. Don't ignore this S or else you're getting rid of all your variables. So I have 3.9 times 10 to the negative 11 is 0.010 times 4S squared. And so I can multiply those together, right? That's 0.040 times S squared. Now I'm going to divide by 0.040. All I did was multiply the 4 times the 0.010. Divide that over. And so I end up with so you get 9.75 times 10 to the negative 10, and then you just want to take the square root of both sides there, or raise it to the 1/2 power, and you get S is 3.1 times 10 to the negative 5. Okay, so in just water, the solubility was, and again, this is molar, don't forget your units, 2.1 times 10 to the negative 4. When you add a common ion, the solubility decreases to 3.1 times 10 to the negative 5. Let's try one more example. Same equation, just now we have a different ion. So let's try what happens when we have sodium fluoride in there. So now we have an initial fluoride concentration. So we're going to start here with 0.010. We don't have any calcium. We're going to add some calcium. We're going to add some fluoride ions. So at equilibrium we have S and 0.010 plus 2S. Now I'm going to take this and plug it in here. And you can stop this video at any time and try to solve this yourself. 3.9 times 10 to the negative 11 is S times 0.010 plus 2S, that whole thing squared. And everything's easier if we don't have this 2S. So we end up with 3.9 times 10 to the negative 11 S, and then 0.01 squared is just 1.0 times 10 to the negative 4. Well, I'm going to divide by 1.0 times 10 to the negative 4 just so I can solve for S. And I end up with 3.9 times 10 to the negative 7 molar. So that's the solubility. So the solubility is just telling you how many moles per liter will dissolve there, which you can get by solving for the concentration of the ions. Whenever you add a common ion, the solubility will decrease.